Okay, welcome to Chapter 5. We're working with modeling with graphs. The textbook I'm referring to is Principles of Mathematics 9. That's the workbook, but it's the same textbook that we're using. This note will work with you if you're taking grade 9 math, even if you're not using that textbook. But the good thing about that textbook is that these page references give you practice work in the textbook, and it also 5.1 etc. follows the McGraw Ryerson book. But of course you can still use these lessons to learn even if you're not using that textbook. Okay, I've learned from the last unit that I'm going to try to make it faster by filling in a few more things before I get started. So hopefully this will make the lesson a little bit faster. Okay, so today we're going to look at direct and partial variation, and we're going to compare the two. So the first lesson is on direct variation. Remember, please, that in the descriptions, you can get links to these pages so that you can print them off, as well as any homework handouts that I provide. So I recommend you print those off first and then follow along. I'm going to try to go a little faster, so you can just stop the tape and catch up in your note-taking. Yeah, okay. Direct variation. Here is an example of direct variation. A plumber charges $75 per hour. This is an example of direct variation because the charge for the plumber varies directly with the hours the plumber works. Write an equation that relates C, which is the charge in dollars, with T, the time in hours, for this example. Well, we know the cost is determined by only one thing: the number of hours he works. He gets $75 every hour, so $75 times H is going to tell us if he works 1 hour, he gets 75. If he works 2, he gets $75 times 2, etc. There's nothing else that's going to determine his cost, and that's why this is called direct variation. With direct variation, I don't know if you can see the whole thing, a relationship between two variables in which one variable is a constant multiplier of the other. So one variable is a constant multiplier of the other. Constant of variation. We often use the letter K to represent that. I'll put that over there. In a direct variation, the ratio corresponding values of the variables, often represented by K, or the constant multiple by which one variable is multiplied. If C varies directly as T, then the constant of variation K is given by K is equal to the cost divided by T, or cost is equal to KT. So K is the constant of variation because it's the multiplier. It's what you multiply one variable by to get the other. So in this example, the constant of variation is 75. That's what we multiply the hours by every time to figure out the cost. So in the first example here, given the table for distance and time, this is a different question. Given the table for distance and time below, state the constant of variation as well as an equation that relates the distance to time, and you're supposed to graph the relation. So here we have time is in S, seconds, and distance is in meters, and you can see that at time 0 there's no distance. Then after 1 second they've moved 10 meters, 2 seconds is 20 meters, etc. So we can see that as time goes up by 1 second, the distance is also going up, and it's going up by 10 meters. So therefore, to figure out K, it is equal to the, remember we said here, you could always figure out K by taking one variable over the other, right? The cost over time. In this case, we would take the distance over the time. So 10 over 1, or we could take 20 over 2, or we could take 30 over 3, or 40 over 4, etc. So 20 over 2, or 4 over 40, whoopsie, 40, you get the idea, dot, 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 and they all equal 10. So that means we know that in order to figure out distance, all we have to do is multiply the time by 10. And you can see that relationship probably without doing that. Distance is equal to 10t. That's how we're figuring it out. So 10 is our constant of variation, because to figure out the distance, we have to multiply time by 10 every time. Okay, so if we graph this, notice you have to write down what is on each axis, so time in seconds, distance in meters, and then you would plot this graph. So I'm just going to plot, oh, actually I should do it in a better color. Let's do 0, 0, and I know 4 and 40 is on my graph, and I know 1 and 10, and I can see if I plot all these points, it creates a line. I'm not using a ruler, but I can see that it continues on. Okay, the key thing here to notice is that the origin, which is the point 0, 0, that point will be on every graph of everything that has direct variation. Every direct variation graph will pass through the origin, and it's going to be a straight line. Okay, next page, we're on to partial variation. So an example of partial variation would be a plumber charges $50 for a home visit plus $25 an hour. This is partial variation because the money that the plumber earns is partly earned by the hours and partly earned by this flat fee. So there's two things that compose the fee that he's getting or she's getting, and so that's partial variation. So if we read that, this is an example of partial variation because the charge for the plumber varies partially with hours the plumber works, but there's also a fixed or initial value that contributes to the overall charge. Write an equation that relates C, charge in dollars, or T time in hours for this example. Well, we know that they get $25 an hour. So for every hour worked, 25H. I wouldn't write it with brackets, actually. I don't know why I did it like that. Oh, let's see how well my eraser pens work. Pretty good. So 25 times H. So 1 hour, $25. 2 hours, $50. 3 hours, $75. So it's 25 times H plus a flat fee. This plumber is getting $50 just for walking in the door. So even if 0 hours are used up, the plumber's still going to get $50. So that's why it's called the initial fee. It's the starting part. So partial variation is a relationship between two variables in which the dependent variable is the sum of, here's the sum, of a constant number, in this case 50, and a constant multiple of the independent variable. So H is the independent variable. If we know our hours, we multiply it by our constant of variation, and then we add our constant number. If y varies partially with x, the equation is of the form y equals mx plus b, where m and b are constants. In this case, m is representing the constant of variation, which is often also referred to as letter k, which is what I've been referring to it so far, and b represents the fixed or the initial value of y. So in this example, what is the constant of variation? Well, the constant of variation is the multiplier on the variable, so 25. And that represents the hourly charge. The fixed or initial value is $50, and that represents the flat fee, fixed charge. It's fixed meaning it doesn't change with anything. It's just always going to be 50 bucks. Okay, question 1a. Complete the table of values given that y varies partially with x. So we know the equation looks like y equals mx plus b. The initial value of y is, on this chart, we can see that when x is 0, the initial value is 6. That's the starting number. The constant of variation we have to figure out. So we're going to look and see what happens. When I increase by 1 here, this goes up by 3. That's going to have to continue. It can't change. If that goes up by 1 again, this will have to go up by 3 again. For partial variation, this will constantly be the same number. It can't change. And then when we go up by 1 again, this will go up by 3, up by 1 again, up by 3, and go up 1 again, up by 3. So this number, every time we go up 1, we go up 3. We know that we are starting with the graph, which starts at the point 0, 6. 0, 6 is the first point on our graph. And we know after that, the y values are going to increase by 3 as the x values increase by 1. So every time this goes up by 1, this goes up by 3. So if we just plot this, we're going to see, oopsie, I messed that up. All right, erase. 0, 6. Start at 0, 6. And then 1, 9. Oh, look, I conveniently picked numbers to make this really, really easy to graph. And it just keeps going up like this, and it's going to continue. And I could draw a line, an arrow to indicate that the pattern is going to continue. Okay, every time I go up 1, I go up 3. Up over 1, up 3. And that's what's happening here. The key feature here is that the first value on the graph, so where you cross the y-axis, is not at 0, 0 when it's partial. That's how you know that at the beginning, at time 0, you're not starting at 0. You're starting at some flat fee or fixed number, which in this case is 6. And then after that, then there's a certain constant rate at which the graph increases or decreases. So that's the telltale sign that you have partial variation when you're looking at a graph. Okay, so let's compare those two. My video's getting long. Hang on. Comparing direct and partial variation graphs. So we've got taxi A and taxi B. The graphs illustrate the total cost in dollars of a taxi fare for a distance d in kilometers for 2 different companies. So this we have is cost in dollars, and this is the distance in kilometers, distance in kilometers. Okay, so on this graph, I can see that at distance 0, when I haven't traveled anywhere, there's a cost of $2. So that must be the flat fee. So I know to figure out the cost, it's going to be something that's multiplying with my distance plus my constant. In this case, the constant is 2. Then I can look and see, okay, every time I increase by 1, I go up by $0.50. And if I go over 1 again, I go up $0.50, 50 cents. I go up 1 again, I go up 50 cents. I'm going up $0.50 every time. So that must mean I'm multiplying my distance times 1/2 or times 50 cents plus 2 will give me this line, the equation of that line, which is also the formula we need to describe what it's going to cost to use taxi A. Taxi B, if I look at the graph, I can see that it passes through 0, 0. And so at distance 0, I don't pay anything. So there's no flat fee with this taxi driver. And then I can see, though, that as I go, I can't really read that one very well. Let's see if it's right. Oh, when I go over 1, 2, 3, 4. When I go 1 over, I'm also going 1/2 up. When I go 1 over, another 1/2 up. Okay, so then I can see that the cost for this taxi is 50 cents or 1/2 times the distance plus nothing. I don't have a flat fee. So that would mean that this is partial variation and this is direct. Okay, classify each as direct or partial variation. Identify the constants of variation for each, as well as the initial fixed value where it exists. So the first example. Oh, sorry. That's referring to all the stuff we just did. So the constant of variation in the first example, which is taxi A, we know the constant of variation is a half. That's the slope. Sorry, that's the M or the K. And the B is the vertical axis, where we start on the vertical axis, and that's the fixed phi. And for the other graph, which is taxi B, we know that M or K is equal to 1 over 2, and there is no fixed part. So how do the graphs differ from each other? Well, they differ because there's a graph that's partial, and it starts at 0, 2. That's graph A. Whereas graph B is direct, and it starts at 0, 0. That's a key feature that's different between the two graphs. What they have is the same, is their rate at which the taxi driver earns money for every hour or every kilometer after the beginning. So they have the same K value, same K, which is a half. And also by looking at the graphs, you'll see they have the same steepness or slope. You can see that this graph, you know, it rises every time you go 2 over, you're going 1 up, 2 over, 1 up. And over here, 2 over, 1 up, 2 over, 1 up. So the steepness is the same on both graphs. And that steepness is determined by the number here, which is the same. And so, of course, the steepness will be the same. Okay, D, write an equation for cost. So we've already done that up above. Okay, the summary then. Direct variation. The equation will always look like y equals mx, and there'll be nothing on the end. M represents the constant of variation. Some versions will use a k. The graph is always a straight line that passes through the origin. This is the essential part. You could also, this is an increasing graph. You could have a decreasing graph. You could have a graph that goes through 0, 0, and it goes down. That's possible too. Partial variation, please ignore the little boo-boo there. I'm talking about this graph here, and the equation always looks like y equals mx plus b, and this here is b. Whatever number is there is the starting number on the graph. B is the fixed or initial value of y, and m represents the constant of variation. The graph is a straight line that does not pass through the origin. That's your key thing you're looking for. Through the origin, not through the origin. Oops, I'm going to stop there. You should stop the video and do the practice sheet, which follows. And then turn the video back on, and I will just show you the solutions after you've tried it yourself. Okay, so turn the video off. Okay, welcome back. Here's the question. You should recognize that this is the average speed, 86 kilometers an hour. K equals distance over time, which is 43 over 0.5, or 86. That's how you can always calculate it. Sorry, I'm going quickly here. D then would equal 86 times t, and you could use that to figure out that when the distance is 250, you would equals 86 times t, and you could rearrange this for time, and you would get approximately 2.9 hours. Question number 2 is the health club membership. The first one is direct, C equals 3n. The second one is partial, C equals 2n plus 8. If you were to use these formulas, you could create some dots for graph A and graph B. Remember, the direct variation starts at 0, 0 and then increases, and in this case it's a steeper graph. The one with partial starts somewhere up on the y-axis and then continues on a less steep graph in this case. You'll notice that A is going to be cheaper before they intersect. So from 0 to 7 visits, that A line is below the B cost. then at the point of intersection, that is called the break-even point. That's when they both, at 8 visits, cost the same price, $24. After that point, B becomes the cheaper one for eternity. You can check this by plugging in 8 visits into the A formula, and you get 24, and into the B, and you also get 24. So you can see, yes, indeed, I did see that correctly. That is the point of intersection, and then obviously by the graph, you can see which one's greater or lower. One thing to think about is do not connect the points, because you can't come for 1.5 visits or a partial visit. So it doesn't make sense in this case to connect the dots. Okay, you should do this homework or the homework in your textbook, and we'll see you next time.